Okay, people getting in. All right, sorry for the people. We are starting 3 minutes late. It was my fault, by the way. I explained Jennifer about this. This is the third session of cryptography, the math behind it. And okay, I let Jennifer to start. I'm gonna today is the last session. So later on, we're gonna have a talk at 11:10 after this session, and in 4 p.m. 10 minutes, we're gonna have the closure of the event. Okay, tell me when you're ready, Jennifer.
Yep, just try to share my screen and getting my screen a little bit bigger. And hopefully,
and you need to close the navigation tab.
Yeah. A little bit smaller.
A little
so
bit.
Get, yeah. Is that good?
I guess so. I mean, I see it well.
Is that okay? Okay, so today really excited. Last sections we're going to talk about quantum cryptography and post-quantum cryptography. So you know, first of all, when people hear about quantum, they will say, "Oh my gosh, it's so hard. Nobody going to understand it." But I can make you understand it because it's not really that hard, and all it is behind it is because we just need to understand the mathematics behind it. Because when you talk about quantum, we are dealing with a lot of really, really tiny particles and photons, and you can't really see it. Excuse me, you can't really see it. So the only way that we can really explain it is by mathematics, by what we call a mathematical framework. So I'm going to explain it that way. So if you have a good mathematics background, like me, I don't claim I understand 100%, but I have a pretty good understanding about the quantum mechanics behind it. So the best known about the best known of practical quantum cryptography is actually the only one type actually. It's called quantum key distribution. Short term we call it QKD. It exploits the principle of quantum mechanics to provide provable security. Now, remember we were talking about computational security because it takes so long to break the system. So it's not feasible for other people to intercept your message and then decrypt the message right away. It usually takes years. That's what we call computational security. And we also see an example for unconditional security, which is the one-time path. It can guarantee your security almost 100%. I would say, I wouldn't say 100%, but almost 100%, but it's unfeasible to use it. So now, today, we're going to look at provable security, because when we talk about quantum mechanics, later on you will see it's just provable, it is secure. It doesn't mean, again, it doesn't mean 100% secure. It doesn't mean, remember I say no system is 100% secure. Well, unless you use a one-time pad, which is unfeasible to use, really. So this is going to be talking about when we talk about quantum cryptography is a provable form of security. Now, there's some other, maybe later on we can talk about post-quantum. It's not really provable security. It's still be in the computational security category, I would say. So just keep that in mind. Even things are quantum, that doesn't mean that it's unbreakable. So this provable security for information exchange is mainly to use with the private key crypto system. And we just learned last time, we know what's the difference between private keys crypto system and the public key crypto systems. So private key crypto system, just a reminder, we have to share a pair of keys. And remember, we talked about that if the adversary or your enemies know everything about the crypto system, the only thing that you need to protect is really the key, right? So that will make a very strong crypto system. Now in here, the private key is the key. So what we want to do is like, we want to exchange that private key, because that, remember, that key has to be shared between the two communication parties. But how are we going to share it? Is can people intercept the key? Once people intercept the key, you're doomed. You can't use the system anymore. People will eavesdrop, and people will know what your secret message is. So that is really primarily used for quantum key exchange. Is making sure that you exchange that pair of exchange that key, that private key, securely. And it is provable due to no one could intercept the message. Since if we do, Alice and Bob will immediately know that message have been intercepted. So this is one of the properties of quantum mechanics. So later on, we'll talk about it, why it is that way. But that's what is a provable security. If someone intercepts your message, the two communication party will immediately know, oh, someone is listening to us. Either they will discard that, or they will just stop communicating. However, it has its pro and con, right? It has the good side, and it also have the bad side. And then it's like it has a high error rate. It's just the quantum mechanics. It's just the basic behind it. It does have a high error rates, and the hardware that you need to produce the photons or produce the laser, they are not perfect. So the imperfection of the hardware, sometimes it will shoot the photon one. Ideally, the photon should go one at a time with a timing in between them, right? And then until you receive it, and then you shoot another one. But sometimes, because of the hardware is not perfect, sometimes you will no photon going out. Sometimes you'll have two photons going out. So that definitely create a problem and a security problem as well. So those are some of the drawbacks, but nonetheless, it is still a really good crypto system, and then it does provide us provable security to do it. And then now that we really need to briefly understand, I will briefly introduce the quantum mechanics behind it before we really go in to talk more about it. So, as I say, quantum mechanics is just, it should not be afraid of it. It's just a whole bunch of mathematics behind it. However, it's very famous experiment to make us realize that, hey, by the way, photons can behave like waves. Just like this double slit experiment is very famous. Sometimes we will refer to the Young experiment, is because it's by Thomas Young, and this happened 200 years ago. So it's not an old thing. Oh, we just discovered it, last century. No, 2 centuries ago, we actually discovered it. So the experiment goal is like, this is your single photon source, just one, like your light bulb or whatever, like here. So and then you have 2 slits open in here. So what the experiment expect is like, okay, if photons is really behaving like particles, we will see maybe a cluster in here and cluster, behind it, because the photon going in only one at a time. So it will only hit 1 slit at a time, not both slits. And then what we find out is really amazing. They were like, wait a minute, it's different. It's not. The reason that we say it's behaving like wave is because they have this pattern in here. They actually have a pattern like this, like dot and light, dot and light, dot and light, kind of like here. And they are actually behave like waves. That's what waves behave like. So that's what they have say, hey, this is a really, really strange phenomenon, 200 years ago. And then you can imagine it's really surprise the people in there. So as I say, quantum is dealing with small particle, very small particle or subatomic particles. And while the classical mechanics, we're dealing with like big things, the gravitational force, the planets, that the orbit of the planets that we're seeing. So quantum is definitely different. So you will, that thing that we can really see, we have to measure, have to do it in a laboratory setting. So that's why we are, having this experiment. And then people say, hey, wait a minute, photons actually can behave like waves. So now this is like completely different story now. So and that is one of the reasons that I would talk about. This is actually, what we could, once they have a waves like that, you have interference right here too. But one of the really interesting thing about quantum is really, mind-boggling. People will say, oh, don't get it. It's what we call superposition. And then if you have heard about this, is a lot of time is the analogy is the Schrodinger's cat analogy. So I put the cat in the box, and then I'm going to have a timer and then release the poison to the cats, right? I don't know why they will make that analogy. It seems too cool, try to kill the cat. But I don't know when the chemical, so to speak, will release and kill the cat, right? It could kill the cat in 2 hours. It can kill the cat in 2 days. So the box is closed, so we cannot see that. So now we're having that in mind and say, okay, the cat probably alive, but in certain time, certain day after, it probably dead. And then, but the analogy is mostly people will say the cat is dead and alive at the same time in the box. So lots of people say, how can a cat be dead and alive at the same time, right? What they fail to tell you is the probability theory coming in handy again. Is 50% chances the cat is still alive, 50% chances the cat is dead. You just haven't had 50-50 chances the cat is alive and dead. So that is what they didn't tell you, didn't explain it behind it. The cat is not dead and alive at the same time, but it's just that probabilistically speaking, that have 50% chance to be dead, 50% chance to be still alive in any moment when we open the box. Once we open the box, right, the cat is inside the box, the chemical, the poison is slowly releasing or not releasing yet, we don't know. But as long as the box is closed, we don't know about, the cat situation. We can only guess, okay, 50% chance is still alive, 50% chance is still dead. Once we open the box, then it will be for sure, right? We can say, oh, the cat is still alive right there. Or you say, oh no, the cat's dead, So this is a very important characteristics of like quantum mechanics here, and then what we call superposition here. So in classical sense, when we talk about bits, right, it's either 1 or 0. I'm sending you 1, I'm sending you 0. I know for sure I'm sending you 1 or 0. However, in the quantum world, so to speak, it is not fixed. So a qubit, we call it a qubit. We're not calling it bits now. We call it a qubit, which is like, the analogy is like equivalent to a bit in a classical mechanics sense. So a qubit will have a 50% chance being a 1 or 0 in its natural state. So basically mean that you're not opening the box. It's just letting the cat do whatever it wants, whatever happened in the box, right? In its natural state, no interference. Interference means that we open the box and we can see it, that's called the interference. And it could be 1 and 0 at the same time. So that's what the analogy coming from. The cat is dead and alive at the same time. So that's what when you hear the Schrodinger cat, and that's what we're referring to. In reality, it's actually 50-50, 30-70, 20-80. It depends on how long the cat is in there. But that's what we usually say, that it can be 0 and 1 at the same time. However, if we no measure or observe, interference to the qubit, that means that when we're opening the box, the natural state of the qubit is going to be collapsed into either 1 or 0 state. So we denote this as a quantum state. So we're talking about states right here, that quantum state 0 or quantum state 1 in here. And there is a different kind of notation in here. It is different than things that you have seen before in normal or other classes. Mathematics, quantum mechanics does have really different kind of symbol that kind of sometimes will drive people crazy because of I think it's called cat or something like that. Maybe it's because of the Schrödinger cat. But when you do what we do inner powder or outer powder, you know, the symbol seems really weird. And I'm not going to go into here because it is a lot of background, a lot of, you know, explanation behind it to do mathematics in a quantum mechanics sense. So we say that now we know that the qubit can be at the 0 state or at the 1 state. So it is possible to, beside collapsing, like before, I mean, when we close the box, we didn't see it, the qubit doesn't collapse or, you know, into a state 0 or 1, like when it's still, so to speak, in the box. What it can actually do is like they can be either 1, you know, that's what at the same time coming from being, what does it mean by being 1 and 0 at the same time? It's basically is a linear combination of the state, denoted like that. This is like a quantum state, psi, I mean, and then they have a alpha with the alpha chances to be a 0 state plus the beta chances to be at the 1 state. And that's what people were talking about, you know, mathematically speaking, that's how you represent it. It can be any state in between 0 and 1, you know, or it can be 0 and 1, and, you know, it can't really be 0. You can be 0 and 1 at the same time, but more precisely, that's how we express that in mathematical terms, that you have a probability of this being at the 0 state, and its probability of beta to have at the 1 state. And remember, we were talking about probability. We learned a little bit about that. And the alpha and beta are complex number. Now we're in a totally different complex planes right here. We are in a complex planes. They're in a complex set of space in here. And then this is basically just signify the length or the scalar of that complex number. When you square it and then plus the beta and square of the beta, it should be equal to 1. That's basically, this is the same theory that we have learned before, probability theory. When you add up all the possible probability, is always equal to 1. So that's no different than that. So it doesn't need nothing to be afraid of. This phenomenon is called superposition. Basically, you know, it can be, you know, at 2 positions at the same time, so to speak, right? And that is when we measure the qubit, we will get, as I explained that already, get a 0 state with probability of alpha to the power of 2, you know, square, and we'll get the state 1, the quantum state 1 with probabilities of beta square right there. So again, I want to encourage you, you know, if you're really interested in it, you know, take a quantum mechanics class. It's not that if you understand the mathematics behind it, you probably have an easier time to understand it. And remember, this is a probabilistic model, because we are talking about probability in here. It's not like what you usually encounter for a mathematical model. That means that you have an input X and you output Y. It's not. It really depends on the distribution of the probability model in here is really based on the distribution in here. So it is a little bit different concept, but you know, if you can remember that, you should be able to understand that. And then when we talk about the other thing, when we talk about, I didn't even mention anything in here, it's quantum mechanics is used a lot of linear algebra, because when you get into quantum computing, this is a completely different kind of like a subject. If you want to talk about quantum computing, we're talking about quantum gates. And when you do a quantum gate to do a transformation from 1 state to another. That's what we do usually, have certain different gates, quantum gates in here, that each gate can represent by a matrix, linear algebra matrix. So that's why there is a lot of linear algebra background behind quantum mechanics. If you do want to take that class, maybe you want to, sharpen up your linear algebra skill, take that class first, and then take a quantum mechanics. Now that's from a mathematical perspective. And I also took a quantum mechanics class from a physics perspective, that we are doing a lot of like Schrodinger equation and the wave equation, the waveform that we are talking about. So that is from the physics side of it. But at the end of the day, it is all mathematics behind it. So we talk about a little bit about block Sophia. So this is really cool visualization of a quantum state here. And you might want to say, okay, what the heck is what is quantum state that we're talking about? Remember that this is the quantum state. And quantum state can be any single, I guess, a position in the block Sophia. Now, we are only talking about one qubit in here, that it can be represented or visualized with a block Sophia. So, and we all know in a 3D plane, right? We have to have 3 numbers to identify a spot right there. And it's based on those 2 angles. And then you can really identify where on the surface or in this sphere that this state exists. But that is just to show you that if we talk about 0 state is here, 1 state is here, there's tons of state in between. In fact, there's infinite many state in a block sphere. Just think about how many dots you can put into a sphere, right? And there's a little geometry coming in now that, that's basically infinite many dots, space in the sphere. So that's why we talk about that. And also, you might say, we say 0 and 1 they are actual computational basis state. That is how they can represent the quantum state in here. They are bases. So that is a little bit coming from vector space, and later on we will tell you what vector space is about. And they are so this is basically can represent the continuums of the state between 0 and 1. 0 and 1 are computational basis states in here, and they form a orthonormal basis for the vector space. And the vector space on the block sphere is not our normal Euclidean space. You all notice that the sphere is curved, and as I mentioned before, and it has infinite dimension. It's an infinite spot places in there, and infinite different spot on a sphere. So instead of Euclidean space, this is going to be the Hilbert space in here. So again, it's just a different concept, a different space that we're working in. So this is all, I think those are all computational spaces. Again, also 0 and 1, they are orthonormal or orthogonal bases in linear algebra or in vector space. It just means they are perpendicular in here. In here, you might say, hey, wait a minute, they don't do really 90 degrees in here, because we are not talking about Euclidean space in here. We're talking about a Hilbert space in here. So it's different, they're curved. So the triangle on a curve, space, and all the angles adding up is going to be greater than 180 degrees. So it's different space we're talking about in here. And as you see, you have complex number in here. We see, how to denote a quantum state, it's like a linear combination of a 0 state and a 1 state in here. And then this is some of the other computational bases in here. And then, 0 and 1 is just not the only computational basis. They actually have 2 more pairs. 0 and 1 happen to be orthogonal. I believe these 2 will be orthogonal in here. You see, because it's straight line, these 2 spaces is orthogonal also. Now, when I say orthonormal, normal basis, that means that the length of that vector is 1 unit. that's why we call it. And not only they are perpendicular, but the length of them is also 1 unit. So that will be really easy for us to, do a linear combination of the two states, and then it will point us to a particular spot on the block sphere, so to speak. So now that means that we need to understand the vector space in here. Remember, this is only 1 qubit. 2 qubit is another story. So we will look at 2 qubit as well. So this is only 1 qubit in here, and it's a really good visualization tool. I think they probably have something online, it can show you where the quantum state are. Remember, quantum state, we use this symbol, a slash, and then a little arrow right there on the right-hand side. And then in there, we usually use a Greek alphabet, and that is, I think it's psi of phi psi. Okay, so vector space in here, the best example you can get is this one, IJK. Some of you might already know if you've taken a linear algebra before. So a formal mathematically definition of a Euclidean space or vector space, any vector space is basically if n is a positive integer, then in order we have an n tuple. So that means that in Euclidean space it's 3, n is 3, right? But it can go to 4, 5, 6, 10, 12, 100, whatever you want. So that will denote the dimension. N is denote the dimension. It's a sequence of n real number in here. In Euclidean space, in vector space, like in block sphere, we do deal with complex number there as well. And the set of all order n tuple is called n space, and it's denoted with this little symbol. R is the real number, and the n is the dimension of the space. So again, when we talk about Euclidean space, we're dealing with real number, and that's how we denote it. And it doesn't necessarily have to be 3. 3 is something that we can visualize, but if you're more than 3, then we cannot really visualize it on a piece of paper, so to speak. We'll have to use our own imagination. So it is interesting that is I heard we were joking about about mathematician versus engineer. One of the things that we come up with, people often talk about, is mathematician can deal with infinite numbers, because in mathematics we usually deal with infinity a lot, right? And then we do mathematics in different dimensions, right? Higher dimension, higher than 3, higher than 2, right? While engineers, they have to build things in the real world, so they cannot handle the infinity or the higher dimension. So it's kind of like a joke, and you think about it, and it's really kind of true, right? We mathematicians is really looking into a lot of like hard mathematics that dealing with a lot of things that we cannot even visualize in the real world or on a piece of paper. So we know how to deal with the higher dimension than the engineers, right? Engineers only dealing with the real world, temperature 0 to 100 degrees Celsius, and obviously, but hey, we can model to the negative 100 degrees Celsius, while in the lab, it will be really, really hard to do it. So that's how we can, it's a little bit different. It's more like a joke. So you can joke about it if you have an engineer friends and like mathematician friends. Mathematician is usually more precise. We like the mathematics more precise, and sometimes in the real world, engineer building is like close enough. That's good enough for them, right? So it's definitely different approach, different perspective in here. Anyway, enough of the joke. And then Euclidean space is actually containing, when we talk about Euclidean space, it's just easier to understand. That's XYZ axis that we usually, probably most of you guys have seen it before. Euclidean space contains 3 unit vectors, IJK. This should be a lowercase I. A point in a Euclidean space, there's a Euclidean space 3 with dimension 3, can be represented again by a linear combination of these 3 unit vectors. For example, usually it's denoted like a, I don't know whether you guys can see it. This is usually bold letters. Usually, sometimes we will put a little arrow on top too to indicate that this is actually a vector. So be careful about that. Just having any alphabet, it doesn't mean that it is a vector. Usually in the textbook, it's either bolded or it have a little arrow on top of it to indicate this is a vector. So this is an example of the vector in a three-dimensional space, R3. And then you can say, 2i, 6j minus 9k. And then 2, 6, 9, if you put a bracket over it and then just take the coefficient in that equation, 2, 6, and 9, and that itself is a vector. That itself is a vector in there. So that's how we denote the vector. And I didn't put in here, but it's almost like kind of like this, instead of like, oh, that's not 3, that should be n. But anyway, so that's how we denote a vector in mathematics. They are also orthogonal. They're unit vector. That means they're one unit. So it's very easy to represent a linear combination of it, and they're orthogonal to each other. So that means they're perpendicular to each other. Now in here, because we are in the Euclidean space, so the angle is 90 degrees in here now. So to each other. So then there's an inner product of any two of this vector inner product. That means it's just more like a multiplication on the vector itself. And then is 0. Later on we'll see what inner product is actually is. And they have the unit length of 1. So they are actually orthonormal as well, right? And they are orthonormal basis of the Euclidean space in here. So let me change it really quick. This should be a lowercase I. And then when we talk about inner products now, so inner products is no different than doing the multiplication of two vectors. But as I say, vectors can have more than one number. So that's why that you're doing the multiplication a little bit differently in here. So let me make a correction again. This is actually supposed to be n, not 3. I probably type it wrong. And again, this is also not 3, and this is supposed to be n in here. So that representing the n space. Oh no, I took the wrong number. Okay, right here. So when we talk about inner product, again, U and V is a vector. Vector can be represented like this. Kind of just like this, but we just take a 2, 6, 9 in here because we know we just like, it doesn't necessarily have to use IJK either. There have been other spaces or have to be orthogonal to each other, but it could be other spaces. But this is the most likely that we'll use for Euclidean space. So if you talk about, let's just be wild, we talk about, n spaces in here, right? N spaces. Then you have a n number in here to represent a vector. You have another n numbers in here in this parenthesis, represent another vector v. And if you want to do an inner product of this, n space, vector space, we basically it denoted like this, like kind of like think about it kind of like a multiplication if you don't have any linear algebra background. But think about it as a multiplication, but because of all these different elements in here, it's just not multiplication straight across. It is like the first element in the U, in the letter U, multiply the second element, the first element in the V, second element, multiply second element, third element, multiply third element, and then we add it up together. And that will get you a number, what we call a scalar number. When you multiply inner product, it will give you a scalar number, a number, so to speak, and just a number. It will not give you another vector. While we use the other one that the other operation that we do in vector space is cross product. Cross product is like usually you have the left hand rule or the right hand rule. That will give you a vector after you do the cross product. This is only an inner product. So that's like two different kind of like multiplication, kind of like, two different operation in the vector space that it will give us different things. But this is how a lot of time that we use to kind of test to see whether the two spaces are orthogonal or not. Because if the two spaces is two vector actually is orthogonal, that means that let me just show that picture, keep showing that picture. That means that their inner product U and V is going to be equal to 0. So orthogonality is basically thinking about like perpendicular in the two-dimensional world. But that it can come across, to any dimensional, as you can see. As long as you have two vectors, we can see that whether they are orthogonal to each other or not by putting it into an inner product and test it and see whether it is 0 or not. So another thing that we need to know about vector space that, for example, we see this right here. Where is it? Right here, where it say with probability right here, like this, right? So this is basically we're talking about the length. Sometime it is denoted to guess what? Pythagorean theorems can be also used in a vector space as well. In fact, I was very impressed. This of Pythagorean theorems that you probably learn it in, I don't know, elementary school or high school. It is a very basic foundation of mathematics. Once you understand it, it can apply to three-dimensional. It can apply to vector space. It's really, really incredible. I feel like that lots of some basic mathematics, you got to understand it, and it can apply to a higher dimension. It can apply to a different situation in here. So Pythagorean theorem in here that we have V and U, again, two vector. They are orthogonal vectors in an N vector space in here with Euclidean inner product. Then if it fit this condition, then you have the length. This is usually denoted the length of the vector. So if you look at this right here, so it's like how long is this length in here, right? Or how long is this length in here? So usually it's denoted the length of the vector. So it basically say that, you know what, if this is two orthogonal vectors in here, and then we have a Euclidean product, with the Euclidean products, we know this two vector is orthogonal, and then we can figure out the length in here. It's basically thinking about, it's two orthogonal, I say it's going to be like a right angle, right? It basically is just the length in between them. It's almost like, yeah, it's exactly like the Pythagorean theorem, but it's in a vector space in here. So if you have the two vector added together and then the length is actually equal to, this is again another typo, it's supposed to be plus in there. So that's denoted the length of the vectors. And you probably learned about it. If it's not orthogonal to each other, what happened? That is have an inequality in here. The sum is usually greater than the adding the two together, or the other way around. I got to think about that. But anyway, if they are orthogonal, the length, adding up together, it will be equal to the individual vectors' length, and add them together. So that's some of the basic of the vector calculus in here that is behind the vector space that we study the quantum mechanics in, special kind of quantum space. And as we can see, the Bloch sphere is only allow you to visualize one qubit. When you get to two qubits, I guess you can put it on the same sphere, you can see it, but it has a really interesting characteristic or interesting properties here that allow us to do the quantum key distribution and allow us to have provable security in the quantum cryptography in there. So we're going to talk about the Bell state or the EPR state, EPR pair. And now we're talking about two qubits in here. So the Bloch sphere can only help us visualize the infinite many states with one qubit. I guess you can put two qubits on the same block. So, but when you get to two qubits, we have two or a pair of qubits, then we will have 4 computational place status in here. So think about binary number, right? When you think about when you only have 1 bit, you have 0 and 1. You have 2 bits, you actually have 4 possible combination here. It can be 0, 0, 0, 1, 1, 0, and 1, 1. So if you have, 3, then you will have 8 possible computational basis or status in here, right? So these are 0, 0, 0, 1, 1, 0, or 1, 1, 1. So if you think about like a classical sense, right? So those are the 4, you have 2 bits, those are the 4 possibility or 4 combination of 0 and 1 in there, in here. And then they form, again, is a computational space. And again, we can represent a quantum state of linear linear combination of this all 4 computational state. It's the same thing with 1 state, is 1 qubit. It's different. It's like 1 qubit, you have 2 states. 4 qubit, 2 qubit, you have 4 states. And then the linear combination is the same thing, right? The alpha 0, 0, alpha 0, 1, alpha 1, 0, alpha 1, 1. Those are denoted as the probability of this state collapse into this state once we measure it. So it could be a 4 state at the same time. It could be some kind of linear combination of the 4 state. Most importantly, we talk about that the Bell states, and this is the Bell state in here, the 4 possible Bell state in here, or the EPR pair in here. That is interesting, important to understand when we talk about quantum cryptography or QKD in here. EPR, Einstein, Polonsky, and Rosen, they're all very famous physicists and mathematicians there. And then they have discovered and then published this phenomena in here. So as you can see, this is just a linear combination of 0, 0, and 1, 1. It's a linear combination of 0, 1, and 1, 0. And then linear combination of 0, 0, and 1, 1. Linear combination of 0, 1, and 1, 0. So all 4 states, they only have 2 states, a linear combination of two of the states. And I believe, I think it's this state and this state is orthogonal. This state and this state is orthogonal. So I think, I'm not sure, I need to go back to my textbook and see. But they are not orthogonal to each other, all 4 of them, but a pair of it is. So just can't remember which pair. The Bell state have the property that upon measure the first qubit, measuring the first qubit, 1 qubit, one obtain 2 possibility results. So when we measure the first qubit, it will have, of course, we often talk about 0 with probability, with half of the probability, 50% chance being 0, and then leaving the post measure state as whatever the beta is, it's just collapsed into just 1 state, right? If you look at right here, if you look at this state, if we measure the first qubit and we know that, oh, it's not there, let's say this one is the first qubit, 1, 1 is the first qubit, and we measure that and say, hey, it's 0 possibility in there. That means that 1 possibility, right? Possibility is equal to 1 will be in this state. So if we just measure 1 qubit, that will actually give us the kind of like what is the state in the second qubit, because they are related, right? They have this correlation. That's what we're talking about. And when you measure the first qubit, it could be 1 possibility, completely, and half of the chance we will have 1, leaving the post-measure state is 1, 1. So that's just like the other way around. It's like, okay, I measure the first qubit, and this is 1. Let's say 1, 1 is the first qubit. I measure it, and it has the probability of that qubit is 1. That means that there's no way you will have this qubit in this state. So post-measure state, that just means that once we measure the first qubit, we'll know what the state is without really measuring the second one, right? So the first qubit and the second qubit, because they're in this Bell state and they have this special relationship, or what we call correlation, that is going to be how we're going to do quantum key distribution in here. But before we talk about that, that's another concept that you need to understand before we really, understand what is a quantum key distribution is about. So This four stated, and this special four state and Bell states is actually known for the four maximally entangled 2-qubit Bell states. So now we're going to talk about what is quantum entanglement is, because that is basically describe what quantum entanglement is. But without knowing these terms or this concept, you're not going to be able to understand the quantum key distribution. So again, just to remind you, when we do quantum operation here, we're not doing operation in Euclidean space. We're doing operation in Hilbert space. So it's another spell. Typo in here. So remember, we're doing in the Hilbert space in here. So quantum entanglement is exactly what I have explained before, just like the Bell state in here. A pair of entangled photons, so it has to be 2 photons, right? It has to be two instead of just one. One doesn't have the entanglement, and we have a pair or 2 photons. They are generated in such a way that their total. It is like physically explaining that is like their total spin is always at sum up to 0, because one particle is found to have clockwise spin on the first axis, and then the other one will be spin the other way and then measure on the same axis. So again, it's measurements coming in. That's what we say when we open the box, see the cat, and that's what we measure. That's what the quantum measurement is about. We actually measure the qubit, and we actually measure in a different axis, basically just different spaces, in the Hilbert space. And then that's why that they have, the measure at the same axis that the other is spinning counterclockwise. So that's why the total spin is 0. One spin this way, one spin the other way on the same axis, and then in the other word, the pair is perfectly correlated, not only with their spin, but their position, momentum, and polarization, and everything. They're perfectly correlated. That's why that we can measure one photon, we can give the result of the other photon. They should be share a exactly same information, except the spin is the different way. But when you have those photons carry information, they should have the same information, and that is how they allow us to exchange information. When we talk about quantum key distribution, it's really we are talking about quantum entanglement in here, and it deals with a pair of photons that is entangled. So without the entanglement, we cannot do the key exchange, because the 2 photons might carry 2 different information. But in this case, because they are perfectly correlated, that's why that we are going to be able to share the information by sending one photon of that entangled pair to another one. So we'll see how we're going to do that. So as I say in here, in order to perform the quantum key distribution, we exploit this quantum entanglement phenomena from the quantum principle in here. All right, so quantum distribution. Relatively kind of complicated, but if you understand the math and the quantum mechanics behind it, and this is just only give you a rough idea. Again, there's a lot of background you need to know in order to go into the calculation and all this mathematical notation in there. It's just a mess. If I try to introduce it right here, right now, won't be able to get the content, so to speak. And a lot of time that it is the notation of the quantum mechanics that is really drive people crazy, because it's not something that you use every day. So traditionally, we depend on the computational difficulty of some mathematical function for a secure communication. I think I said that before. So QTD is actually rely on quantum entanglement to provide the provable security for information exchange. So remember, measuring a entangled photon or an unknown quantum state will result in the collapse of the quantum state. So the main vehicle that we use for the key distribution, for the quantum key distribution, is this BB84 protocol. That's another one, I think it's called E91 protocol, but just show you one protocol is kind of give you an idea how it works. But there is some other protocol out there, but it's not a lot. I think that is only two I know, or who knows, maybe someone's already invented another one as well. Quantum research is slow, but is also, you know, have groundbreaking results sometimes that you kind of have to keep on top of it and see what's going on right recently. But as this protocol indicated, 84 is actually invented in 1984. So it's an old protocol. And again, quantum mechanics, we see the split, double slit experiment is back 2 centuries ago. So it is a old kind of like, you know, principle out there, but just pretty recently we find that it had application in cryptography. So this is, I think the table probably better explain it. But I'll go through this and just to let you know. So you have to choose a certain length of the bits, because you half of the bit is not going to work. As you can see, you send this, measure this, you can only get half of the information here. So your length has to be a certain length. Your length has to be certain length to making sure that you communicate the information to your other communication partners, and making sure that you have enough length that you make sure that the other partner, your partner, get the key. So that's why we have, say, 4 plus delta n random data bits. That Alice chose a random bit string B. She encoded each data bit 0 or 1 into a corresponding bit of B. Or like a plus and negative. So basically, this is talking about the axis that we were talking about, how we measure the quantum entanglement pair photons in here. So they just choose encoded it into different bases, so to speak. So Alice sent the resulting state to Bob. So this is you choose a bit string, n bit string B in here, and hold each one. So this is basically Alex showed random bits in here. It encoded in a certain bases in here, and then it sent the space to Bob. Bob received those space. They announce this fact and they measure each of the spaces in X or Y basically at random. So Bob doesn't know what basis that is either 0, 1 or plus and minus the space. So this is how we denote it, is like what they call a plus or a cross. Those are the spaces that you measure or axis that you measure the qubits from. So Alice just randomly choose it, and then polarizing it, and then when Bob receives it, he just like randomly chose, and then they tell Alex about it, and then Alex say, no, this is not what I use. You know, as you say, if they use the same what do you call it, basis. Yeah, I guess we'll just call it basis or axis. Either way, it's the same thing. So when they choose the same basis to measure the qubits, they will get the same result. But if they, in the second qubit, it says Alex sent a 1 measure in the cross basis, and then the Bob used a 1 basis to measure it, you will not get the same results in here. So and so on and so on. You can see that 1, it doesn't necessarily has to be this basis. It can be a cross basis. 2, and then you measure the same. If you use the same basis, then you can be the same. So that's how that you do the BB84 protocol in here. So Bob got the message. Alice say, okay, this is what I chose. This is what basis that I measure, and Alice and Bob discard any bit that Bob measured in a different spaces, so which is those empty spaces. We're not going to do that. And then Alice prepare with high probability there should be at least 2 n bits left. If not, we're going to abort the protocol. So that's that we need to choose enough length that you get the message across, because like probably like half of that or more than half of that is not going to be the same, usually 50-50 actually. If not, then it's like no way, we're not going to use the protocol. We're going to send a whole new message again, whole new bit string, and a whole new basic different spaces again. And then they will keep the 2n bits once they're done. Now let's select a subset of n bits that will to serve as a check on if interference. So when you check the interference, remember we talk about that this is a provable security. So when you check, you don't know when you communicate it, you know that if you eavesdrop, if you measure your photon, or if you collapsing your photon measurement, that means that collapsing your photon, you will immediately know the state. Before you don't know the state, right? So that's why they choose randomly choose a subset of n, and they're going to monitoring those photons and see whether it has been interfered, and then tell Bob which bit that she selected, right? And Alice and Bob announce that and compare the value of the n check bits. Those are just checking bits. Usually like half of this string is actual check bits. And if more than an acceptable number disagreement, they will abort the protocol. That means that, hey, someone's eavesdropping, someone's measuring it, collapsing all the state into 1 or 0. So we're not going to, it's not secure. Someone got a message, let's do it all again, so to speak. So Alice and Bob perform the information reconciliation and privacy amplification on the remaining n bit to obtain n share bit of key. So that's why that, it's a provable security, because you can actually monitor whether people are eavesdropping or not. If they eavesdrop, you will know. So that's why it is exploiting, again, one of the properties of quantum mechanics in here. And that's why people can be able to figure out whether someone is eavesdropping or not in here. So this might be a good break to stop to see whether anybody have any questions so far.
Is there any question?
I don't see any question typed in the box.
Nope. No questions in the chat room. So
fantastic. I think that means you guys all understand it perfectly, right? Then we'll move on.
Let's see, one question at one, twice, all to Jennifer again. So, okay, keep going, Jennifer.
Okay, great, fantastic. We'll keep going. So now this is how we do what we call quantum cryptography, and usually it's really referred to quantum key distribution only, and it has been used for the protocol is invented in '84, right? I think the first demonstration successfully for quantum key distribution is in, of course, Austria, a transition between bank, I think, or something like that. They can demonstrate that, the practicality of it back in like 2006, 2001, somewhere in that time frame. So it's been used in 20 years probably. I know in European countries they use it a lot more than in US. So because I think we have really strong crypto system in the US, so that might not be necessary. And the other reason is like it's expensive. As I say, the devices or the hardware, you need to have special hardware. You have to invent it, or you have to have the photon source to emit the photons. So so it is quite expensive equipment and specialized equipment that not everybody can do it. So only a few companies, I think, in the world that have that capability, and then doing the quantum key exchange. So now post-quantum cryptography is actually nothing to do with quantum mechanics. So a lot of people kind of like misunderstand it. Oh, I'm interested in quantum mechanics. Let's study quantum post-quantum cryptography. It's just a post-quantum, as you see, is after, right? After the quantum world. So that is like the reason behind that we do post-quantum cryptography is, what if people have quantum computer. As I was mentioned before, quantum computer and quantum computing is a completely different set of mathematics. Also, you're dealing with quantum gates, you're dealing with a lot of linear algebra, transformation and stuff, Hardeman transformation, polymetrics, and you're dealing with a lot of different things in here. But the reason that we have post-quantum cryptography is like we're assuming that, oh, what if there is a quantum computer right here? As I said before, it's just a quadruple speed up. It's not really, oh, cryptography is going to dead, it's going to break every single crypto system in the world. It's not quite that. So it's not, that quantum doesn't have that quite, powerful magic, so to speak. It's not a magical term. It's not a magic bullet, so to speak. So it has its limitation, but to prepare for that, it does break some of the system. It does break some of the crypto system. Anything that we say, even take a year to break a possibility to break the crypto system or the encryption, we just say, oh, it's not safe. We better look for something else, because then, especially right now, have the internet, everybody will know about how to break the system. So that's why post-quantum cryptography is coming in, is to prepare that if we have a quantum computer, we need to have a new set of, encryption functions, or invented new crypto systems, to use in the present of quantum computers. So as I say, it have nothing really to do with quantum mechanics or its principle. It's basically classical cryptography in here. It is still based on computational hard problems in here. I have two examples in here. I don't want to go into too much detail, because again, there's a different kind of mathematics, every time that you talk about cryptography, because they are based on a really hard computational problem that is deemed to be quantum resistant. What do they mean by quantum resistant? Is actually what they mean is like there are no known quantum algorithms there that could break the crypto system easily. So it is not mean that, oh, we can resist the quantum computer. It can stop the quantum computer, break the code. It just there is no quantum algorithms out there to prove that, to break the crypto system, to solve, so to speak, to solve the mathematical hard problem behind those crypto systems. So currently we have two quantum, very well-known two quantum algorithms here. There are others, but this two is the most famous or well-known quantum algorithms out there that they think it will break some of the crypto system in here. What we call Shor's algorithm or Gopher algorithm. Again, it's way too complicated to go into those algorithms in detail. You just need to know about Shor's algorithm. It actually can solve the discrete lock problem. Remember, Algorithmic crypto system is based on the discrete lock, and Shor's algorithm is actually really good at solving the factoring problem. So basically, if you're factoring the big prime number, it can probably help as well. But it's particularly used to solve the discrete logarithm problem in polynomial time. Because if you use a classical computer, if you use the classical way to solve a discrete log algorithm, it's going to take exponential time to solve it. So that means that it's really hard. And in fact, a lot of the crypto system is based on those mathematical computationally hard problems that it takes a lot of time. It takes exponential time. So we don't need to worry about that. And that's why that we call that computational secure, right? But in here, instead of a exponential time, we actually can solve this problem with polynomial time. So now we say, oh no, that means that it can, instead of taking forever, it takes a limit of time that you can actually solve that problem, so that's not safe anymore. So we are not going to use discrete algorithm anymore. On the other hand, you have the Gopher's algorithm that can perform exhaustive search. When you do a brute force attack, that means that you search for every single possible keys and try to figure out the private key, so to speak, right, in a private key crypto system. And if you do an exhaustive search with a classical computer, same thing. It might be going into exponential time. But in here, you can perform the search better than a classical computer could. So usually they will have a quadruple speed up. Usually we talk about quadruple speed up in the search in using quantum algorithm. Now, this too is very famous algorithm, but it's very particular to solve only one problem, right? So as long as there is really lack of quantum algorithm to solve every single problem, or to kind of like your normal computer that have a general purpose. That's what it can do everything for you. So that's why it's that limitation of the quantum computer too as well. It doesn't mean that when you say quantum computer, it doesn't mean that, you know, it's just like our normal computer, it have general purpose. Quantum computer with a very specific quantum algorithm that can only solve one set of problem, one group of problem in there. So that is why that we have this post-quantum cryptography that people say, okay, we cannot use the discrete log problem anymore to form our crypto system. We cannot, you know, there is an exhaustive search for the key. So we need to be careful about that. So maybe we need to make the key size bigger. It will be harder to solve and harder to find, and even at a longer time to find. And that's why that is sometimes we go to a 2048-bit size key, you know, for some of the crypto system in here now. So lattice-based cryptography is one of what so-called quantum resistant. I would say, quote, you know, it's not really quantum resistant because that is a again, it's based on a very hard mathematical problems. It's a lattice, like it's just like a whole bunch of dots like that. And then it's really have a particular structure in there, and it's n-dimensional space. Again, we are going into high and high dimensional in here. It doesn't necessarily have to be 2 or 3. And then the definition, the formal definition is like giving n linear independent vectors. So we just learned about vectors, right? They're linear independent. Basically, they're orthogonal. They have they're independent from each other. They're not you cannot have a linear combination of the vectors from the other vectors. So basically, they're basically orthogonal. In here, in the vector space and vector space, the lattice generated by them is a set of vectors like this. And then again, this kind of funny looking L is just indicate is a ladder space. And then you have this ladder, and then basically it's a linear combination of 2 numbers in here, right? So the vector B1 to Bn are known as the basis of the ladder. So it sounds very much like the vector space that we just learned. We have a basis, we have a vector, you know, we have, and then we have, and those vectors form the basis of the lattice. So why this is a hard problem is because there's 2 hard problems come with the lattice. When we study lattice. The lattice space cryptography is based on presumably hardest problem of lattice problem. So one of them is called shortest vector problem. The other one is called closest vector problem. So the shorter vector you probably kind of guessing it. And I have a ladder space in here, in n vector space in here. We have a self vector. It's not an empty set of vector. It's not empty. It's not 0, basically, that means. And then the length of that vector, right, is minimizing. So basically, I'm just like to find, and such a vector is called the shortest vector in the lattice. So given you at that ladder space, or ladders in the n vector space in here, how are we going to find the shortest, you know, lattice, shortest vector in that lattice? So that's what the shortest vectors problem is. It's really apparently and actually really hard to find the shortest vectors in that vector space. So again, it's almost like out of like, this is like good visualization, but again, this is only a 2, you know, dimensional space. It can go up to a different dimensional space. It can go up to 10, 2, 3, whatever, and it's just like, you know, and that would dictate the vector's length in here. So the other one is like, okay, I have this ladder space, or ladders in the vector space in here is spanned by a group of ladders, a basis. And it is, and then I happen to have another vectors outside this ladder base, a basis for a letter L, a lattice in the n vector base, and that there's a vector is outside. It's not in this lattice, but it's outside the lattice. Now I need to find that this lattice, this vectors W, and the V lattice, which is in the lattice base, that distance is minimized. The closest, that's what we call it, closest vector in it. So basically, we're talking about the distance in here. In the shortest vector case, the distance is within the lattice space, while closest vector is I have a vector outside the lattice space, and I need to find the shortest distance to that lattice space, a vector in that lattice space. So basically, pretty much like the same problem, finding the shorter distance. And again, it is a very, very hard problem to solve. So from here, now we know a little bit about the lattice, the background of the lattice. So we can talk about this called NTLU. It is a public key crypto system with NTLU equipped is the current version. And so usually you will hear people talk about this crypto system in here, or encryption algorithm in here. It is a very fast crypto system that's easy to implement. That's really the key. You know, when you have the crypto system mathematically defined is one thing, implementing it is another thing. So it has to be easy to implement, it has to be fast, so we can, you know, again, it's all the same principle that we learn about cryptography, crypto system, is all applied to post-quantum crypto system cryptography as well. So again, post-quantum is just a fancy word. It is no different than just finding another mathematically hard problem, and based on that to form or invent another crypto system in here that have no known quantum algorithm that can easily break or solve the hard problem in here. So nothing to do really with quantum mechanics and stuff in here. So this is okay, I talked about that. And so they have three parameters in here, M, P, and Q, which they are fixed integer computations performed now. Again, it's in a ring. The computation performed in the ring, and this is a particular ring that they're talking about in here. So this is very similar to the AES. They have a particular field that we're talking about generating in. So I will imagine that this is going to be a pretty strong crypto system because they have a really strong mathematical algebraic structure behind it. So to go into a little bit detail, P and Q is usually, denote a prime number in here. So this is the formal definition of the NTLU encrypt crypto system in here. Suppose we have PQ and N. Again, they're integer in here. They're fixed. Q is significantly larger than P. That's what this symbol means. Q is significantly larger than P. P and Q are relatively prime. And this is like all kind of like familiar, right? We kind of know all this before with RSA crypto system. And P is odd. So in here, we do have another restriction parameter. P has to be odd, and the M is a prime number in here. Typical value for this parameter P is equal to 3, Q is equal to 2048, and N is equal to 401. So we're going to let a plain text is in this set. It could be N. Again, remember, we are talking about vectors in here. So everything is N dimension in here now. So, and then the ciphertext is in this field. Is that a field or ring? I think this is a ring. And then we chose, again, it's N dimension. And then we chose F and G. F and G happen to be a function. F and G are function in this set as well. And let F is equal to 1 plus P multiplied by F. So a function in F is equal to a prime, P is a prime number, an odd number multiplied by the function and plus 1. And then let G is going to be, this function is going to be the P multiplying G, the function. And the H, we define H. H is your public key here. H will be the reverse of that function F multiplied G in modulos Why this is S is because remember we're dealing with vectors in here. There are more than one number. We are multiplying modulo Q in here. So the associated key T set will be F and G. And where F is the private key and H is the public key in here. So this is a little bit similar to the RS8 that we were talking about as a pair of key. It is a public, this is a public key crypto system in here. So we are going to have a pair of key F and G. One is private and one is public. The way that you do the encryption, you encrypt the plain text by multiplying the R and H, your public key right here. And this is I say multiplying, but it's a special operation. It's called convolution operation. It's basically adding two functions together. And you can see R is actually also in this set as well. R is the same as F and G is the same function. So R is a function itself. And then you add it to the H, doing a convolution operation with H and plus the M. And that is how, and mark Q, and that's how you get the ciphertext in here. To decrypt the ciphertext in here, you will basically have the private key, right? You use the public key to encrypt the message and use the private key to decrypt the message in here. And you have modulo Q and P. And don't even ask me how to do those mathematically. It's very, very complicated. We are not going to have time to go into it. The key takeaway is this is a public key crypto system. You have a F as the private key. As usual, you use a Y private key to encrypt the message, and you use the H public key to encrypt the message, and you use a private key to decrypt the message. And in here, again, we have a new mathematical concept that we need to be familiar with to really understand how these crypto systems work and how to add, two functions together. But you might already know how to add two functions together. So that is what we call lattice-based cryptography. And it is an example. There's probably other crypto systems based on that as well, but this is probably like the most well-known one. And I believe this might be going to be one of the standards for post-quantum cryptography in the United States. As I mentioned, we have a government agency to set all the standards. So that might become one of the standards now. And then the code-based cryptography, maybe I can do a new page. So the code-based, and again, is bringing in another branch of mathematics in here, and it is called coding theory. So a little bit about coding theory. Coding theory is a study of method of efficiently and accurately transferring information from one place to another. Sounds very much like cryptography, but remember, it is coded message. It's not encrypted message, right? This encoding and decoding, it has to be doing really, really fast. And it is usually dealing with signals, like when your television, during the old time, right now we all use cable now, but during the old time you use antenna, you use the signal, and that's how we need to encode the whatever message in there. It has to be fast, it has to send it to you, and then your television or your whatever device will be decoding the message, and then now you got the picture, and you can see television, watch your show, watch your favorite show. So this is still a problem with detecting and correcting. The other aspect of this, different than cryptography, is like correcting, because there's a lot of transmission. We have errors in it. So we're correcting the error transmission error code in here by the noise, because when you send the message source in here, you encode the message and then you go through a channel. The channel is most likely have a lot of noise in there, and then creating the errors in here. So when you decode it, you got to correct those errors, and then you can receive the message. So again, this is not cryptography. You're not encrypting the message. You're basically just encoding the message so you can send message or send your signal more efficiently and fast. Because when you think about it, you have this like I don't know, signal emitter on a hill, You're sending the signal, everybody has to receive it almost instantaneously and then decode it instantaneously to watch the show, right? Broadcasting those signals, thinking about the TV station, the radio station, and that's what it is all about, coding theory behind it. We want to construct codes that will maximum the transfer of the information per unit time. We need to be fast, right? And yet at the same time, it has to be accurately transfer the information. That means that we need to have the decoding will have error correction, in there. So making sure that you receive the when you want to watch, I don't know, American Got Talents or Ecuador Got Talents, you want to watch the right show. You don't want to have error image on there. So again, this is like basically processing the signal in here. So let k and n be the positive integer. K is less than or equal to n. A linear code, that's what we call it, a linear code, is a k-dimensional subspace of this C is integer, right? Integer, and this is binary. And the code and decode is always sent in binary form, but it's in the n space, but it's a subset of this space. And the vector space of all binary tuple. So this constitute of all binary tuple, but we just want to be the linear code is the subset of that. So a linear code n and k, code C, a code, is a k-dimensional subspace of that, okay? And it generates a matrix for a linear nk code is a k by n binary matrix whose rows form the basis of the code or basis of C. And distance between two linear code is called Hamming distance. We're not even going into the what is Hamming distance, but the two code, it does have the distance. That's what we're talking about sometimes when we do this kind of mathematics or signal processing. There's a lot of mathematics behind it as well. So as usual, this kind of cryptography is based on mathematically hard problem. In this case, we're based on non-polynomial hard problem. So this is a set of problems that we say the classical computer cannot solve, right, in a polynomial type. That's why it's a non-polynomial hard problem. So this is a whole new set of problems that they're based on. And one of the example in here is Lattice is a public key crypto system. The private key is random bit of irreducible as go per go. Whatever, however this code is formulated, is irreducible. And the public key is a random generation of the matrix of random permutation version of the code. And the ciphertext is a code word to which some error has been added. So the way that it kind of works is like you have the ciphertext is basically I'm adding error code in it. So unless you can be able to correct those errors, you will not be able to receive or figure out the plain text, the original message in here. So again, it's very complicated. You need to have a lot of coding theory background. We're not going to be in the detail, but kind of like just at a very high level, how it is work. It is dealing with error correction code in here, in this case. Wow, so again, I hope you see that there's a lot of different kind of mathematics in there behind cryptography. And you do, as I say to Ken Danny at the beginning, a lot of the cryptography done is by computer scientists. They just need to be able to figure out, as you say, it's very complicated. You're not going to do this by hand. And usually it's a computer program to do it. And when you send Gmail, 95% of Gmail is encrypted. They do it at the back hall, at the back, and you don't even see it. You don't even see how it works. So, but as the threat of quantum computing or quantum computer is coming into reality, we need to continue to inventing new crypto system that is based on different kind of hard problem. And if you on the other side, if you want to break those systems, you might want to go into quantum mechanics or quantum computing and see whether you can invent a new algorithm to break those hard problems. So there's a lot of mathematically, hard problems that, who knows, maybe one day it will break by the quantum computer. Breaking by quantum computer means that there is quantum algorithm to solve those hard problems. So as you can see, That is usually how cryptography works. So that is a very common, concept out there. Again, I'm not going to be into detail. It's a computer program sometime, a computer application. But I'm going to introduce that cryptocurrency. Again, it's not, when they say cryptocurrency, maybe they use, what they actually means is like the information in there is actually like using hashing. It's not really using cryptography or encryption. Maybe they will use some form of encryption, but not in the currency itself. The currency itself have nothing to do. You cannot encrypt the currency. You can only hash the currency, and to making sure that it's integrity of the data that we worry about in here, right? How much Bitcoin that you have is much important than hiding how much Bitcoin you have. And in fact, you cannot hide those information. You have to make it public, and people have to verifying it. And that's how cryptocurrency works. So how, again, as the beginning of the section, I say cryptography and hashing, sometimes people mix it up together. So you got to be careful thinking about cryptography is really hiding the information. We want the confidentiality of the information, while hashing is like trying to protect the integrity of the information in here. Two different objectives, very similar. They probably use a similar, what we call cryptographic hash function. So, it's related to cryptography, but it's a two different objective in here. Very common, very common. People mix these two things up, and then thinking about their equivalent to each other. They're not. So cryptocurrency, again, have nothing to do with cryptography, the currency itself. The goal here is not to protect the confidentiality of the data, but is to protect the integrity of the data. In this case, it's the amount of digital currency that you have, such as the three most famous cryptocurrency I heard is Bitcoin, Ethereum, I think that's how you put it, Ethereum and Dogecoin. Bitcoin, Ethereum, and Dogecoin. That's three that I heard about it all the time. And again, cryptocurrency is like a different cryptocurrency. They are all not the same. It decentralized the cryptocurrency control. So instead of the federal government controlling the currency, the dollar bill, you have in your hand, this is completely out of this centralized control. It completely depends on a group of people, a large group of people to control the cryptocurrency in here. So how it works is like each cryptocurrency is actually a blockchain. They use blockchain technology to form a ledger. So blockchains, we can explain a little bit later on. And it is the cryptocurrency transaction database. So it's just like when you go to the bank, you deposit $15, you deposit $100, you deposit $2,000, right? Those transactions is actually locked, forming a database, and this database is the blockchain here. So the information on the ledger is public, it's not encrypted. As I say, the cryptocurrency itself is not encrypted, it has to be public. And this ledger or blockchain have that transaction database in there, contain a list of record of how much Bitcoin how many Bitcoin you actually deposit in there. So they have a list of record called blocks. Each block is a record. And they are continuous growing. Each block is continuous growing when you have a new person or a node join the blockchain. So basically, you can imagine that, let's say, for example, we have 41 people here, you all line up. Each of you guys is a block, right? Each of you guys have the block of information of the transaction. And each block is kind of related to each other. We kind of holding hand with each other, and then they are all forming a chain, right? And this whole chain have all this transaction information in there, and have all the record of the transaction of the Bitcoin in here. So every transaction within the Bitcoin is known by all people. 41 blocks, 41 basically nodes, block. You don't have to, your transaction doesn't have to be linked to a person. It's usually we talk about is to a node. A node can be a computer station or whatever, so you can remain privacy. You can remain, that, I don't want everybody to know that Jennifer has just deposited 200 Bitcoins into the chain, but I can just be really discreet and say person 1 or person 41, person 29 or node 29 have deposited 200 Bitcoin into the chain. Now that transaction is known by everyone. Everyone know that you're depositing $200, and that blockchain will have that record in here. So what it happened to be that I'm announcing that, hey, I'm deposit 200 there. That information might be encrypted. That broadcasting that information might be encrypted, but the currency itself is not encrypted. So it might be secret. I don't want everybody to know that I deposit 200, but in some form, I have to everybody know that I'm making a transaction on the blockchain. So the transaction is verified by others on the blockchain. So person number 2 deposit 200 Bitcoin, person number 29 and person number 38, they're going to verify it on the blockchain. So once it is verified, it's most likely is using a hash function, that making sure that the integrity you say 200 is it really 200, what if it's or it could be 20 and you claim it 200. So that's the integrity of the message that we are dealing with in here, and we're going to verify it, record it, and then put it back onto the blockchain. Once it put back on the blockchain, nobody can change the information on the blockchain there, and then and that's why that they say it is a security by design, this blockchain, because once you do a hash and then put it back onto the blockchain, and that information is verified and is hashed with the message hijacks, right, to ensure that the integrity of the message is right, the transaction amount or whatever information is right and on the blockchain, and nobody else can change it. And the way that you use it, the way it works is like, remember, the blockchain is a whole bunch of people, whole bunch of nodes, right? We need to have 70% of the people on the blockchain that verify the information to prevent collusion. If you only have if you could collude, hey, I'm going to deposit $20, but please say it is $200, 200 Bitcoin, right? You can collude with the people, but we somehow figure out that if 75% of the people agree and verify the information, that is going to be correct on the blockchain. Once it put on the contract, it will prevent the collusion in here, that nobody can be colluded. If 50% is not enough, we figure out about 75%, usually 75% of the people on the chain verify the information, and the incentive that people get from verifying those information. I verify, node number 21 deposits 200 Bitcoin, and that the incentive we gave people to do it is they also get a reward. So the reward, as a cryptocurrency. So that's why that it motivated people to do it. So as long as we have 75% of people on the chain doing it, then those are good, accurate information, and then we can prevent collusion in here. So it's a very, very new technology. I didn't really learn it. I just know a high level how it works. I do know that people, this is only digital currency we are talking about. It is not the physical, things that we are talking about. You can hold, you can smell, you can I don't know, you can touch the money. This is just digital currency. It will get lost. It will get it will get lost in the cyberspace. It's nothing physical. It doesn't have physical value on it. It is more like a stock, right? And in fact, you can just see, it depend on, I guess it's depend on supply and demand, and the value of the Bitcoin can go up and down. One Bitcoin can worth, I don't know, $10 today and $200 the other next day. And that's what the story behind the Dogecoin. I think someone make some kind of comment, or some people, I don't remember what it is. It's all of a sudden like one day it jump a lot, it go up a lot and then go back down. So it's more kind of like, it's very like fluctuated, it's not like the real currency. $1 actually mean $1. One Bitcoin can mean, have a different value. And then again, it's a different cryptocurrency in here that, you could have, you buy some Bitcoin, you buy some Ethereum, or you get some Dogecoin, you know, you can, it's all different. Basically, the different meaning that they have a different blockchain, you know, to govern their transaction in here. So that's why that I can see in the future that people were talking about that how to, like, well, the purpose of it is decentralized, right? So a group of people, I don't know, 20,000 or 1 million, those are the people on the blockchain themselves governing this cryptocurrency. It's not governed by the government, it's not governed by any other entities, you know, but it is really governed by the group of people. Again, 75% of the people has to agree and verify the information. So to prevent collusion or to making sure that it works. If nobody doing the job, you know, the currency doesn't probably worth anything. So it's very different concept. I think Bitcoin is very old. I think it's like, I say old, I think it's invented in the 2001 or 2006, that time frame. I don't remember the exact day, 2003, 4, that. So it's about 20 years old. And then there's a lot of new things coming up. And then the newest one, I think, is Facebook. Facebook want to have their own cryptocurrency, but they want to link it to something actually valuable. So they actually have kind of like, oh, that actually means something. In here, this is all digital currency. It doesn't really mean anything, you know. In fact, a lot of time you heard about ransomware. People, you know, lock up your database, you know, on your computer. You cannot access it unless you pay a ransom in Bitcoin, and that's what cryptocurrency is coming from. It can all transition within digitally, so you don't have to go to the bank. You don't have to like some of those like movie, you know, carry a bag of money, give it to the you know, to the other people. So this all can be done on the digitally. It depends on the application. Again, you know, different company or different Bitcoin will have a different kind of application you'll use to do that. So that is pretty much conclude about like what cryptography or anything related to cryptography is about. And I want to talk a little bit about cybersecurity. As I mentioned, I'm in the cybersecurity field. Cryptography is just one of the one branch or one principle of cybersecurity. Cybersecurity is a lot of different things. In fact, it's interdisciplinary, you know, in here. When you talk about cybersecurity, this is a kind of like a normal definition. Cybersecurity is an application of technology, processes, and controls to protect system, networks, program, devices, and data from cyber attacks. It aims to reduce the risk of cyber attacks and protect against unauthorized use, unauthorized exploitation of system, network, and technology. And I will add that, I think I forgot to add that is also protect not only the unauthorized exploitation, also protect the mistake that people do. Sometimes they accidentally do certain things that act like a, you know, adversary is attacking your system, but sometimes it's actually a legitimate people make mistake. We want to protect that too. And in fact, one of the way the hackers, you know, try to hide themselves is hiding behind the legitimate mistake. Sometimes it's really hard to tell whether this is a legitimate mistake, a user use, or is it actually an unauthorized exploitation of the system. So that's why that this field is very interesting, very challenging. A lot of, I would say about 50% of the people in cybersecurity is actually from the technical background, the information technical background. Sysadmins, system administrators do a lot of security as well, doing access control, making sure your password is so many, you know, so long and stuff like that. That are all, you know, part of cybersecurity. So usually cybersecurity, we talk about the boom. It means that, you know, you have a data breach. You probably heard about it all the time. Ransomware, SolarWinds recently have a data breach. Many years ago, you know, I think Sony also have a data breach, and then someone got into it, and then, you know, figure out all the salary of the actors or actresses or something like that. All the email was leaked out. So that's what we call the boom. and to protect the hacking or exploitation of the system or protecting your data. A lot of time you probably hear that, everybody probably know this about firewall. Your computer probably have a antivirus programs running, making sure there's no antivirus coming. The email, Google, again, they're filtering suspicious email. They might warn you this email is suspicious. And then IDS and IDP is intruder detection system and intruder prevention system. Sometimes you have some type of system you can prevent that, have that boom, that data breach in here. More often we talk about left of the broom and the right of the broom. The left of the broom is usually if you're preventing the boom, you're proactively making sure that your system is secure, and then try to do due diligence, making sure that you have security measure in your system to prevent the boom. Now, again, this is very much like cryptography. It doesn't matter how much security or how many security controls you have, or how you have vigorous security measure on your system. It is only a matter of time. Every single system, computer system, networks will be break. People will find a way to break it. It is really a matter of time. Also, a lot of time that we are saying the data breach, you cannot prevent it. It's only a matter of time. You can only talk about how much time until you have the data breach. That's why you have the continuous monitoring your system. On the left of the broom is you're trying to preventing those data breach, and I'm on the left side of the broom. So risk assessment, vulnerability scanning, penetration testing, you hack your own system and see what is a vulnerability there, and you can better prevent the system to be exploited or to be hacked. And compliance review. Sometimes your system has to go through a rigorous compliance process, and that's what we were talking about too. And then that's just some example of it. Another one will be another thing will be system development. When you develop the software, you develop a system, you got to think about security. If you have design security by design, like the blockchain is security by design, then you most likely will be better off without that. Another fun, what I do, technology, R&Q technology, research and development is also trying to prevent the boom. So in here, what else? A lot of engineering work is here. When you're engineering the system, you have to think about, if you can think about security in mind, that will definitely get you a longer way. And the right side of the broom is like, oh my God, okay, someone hacked my system. What am I going to do? And as I say, it happened. It's just a matter of time. It happened. So a lot of companies will have incident responses. So once it happened, everybody probably working 24/7 and try to restore the system or try to figure out who is actually hacking the system. Then you become digital forensic. You got to go in and say they left some digital footprints in there. Got to investigate it. Cybercrime has been committed. Got to investigation. That will be also right at the broom. Security operation also, right? Once you have the boom, oh my gosh, everything under the table. Now I need to have, usually you will have a response plan, an emergency plan. If something happened like that, what are you going to do? So that is a security operation. That's also right side of the broom. Remediation, okay, that happened. Well, am I going to salvage the rest of the system there, or trying to making sure that how much time I'm going to try to make sure the system is up again. So did I say something? Okay, yeah. And a lot of time that if you have 3 security objectives in mind, you have confidentiality, which is cryptography. That's why I say cryptography is only part of the cybersecurity. Security is not everything. You also need to do integrity. You also have integrity in mind, just like the hash function. You got to make sure that if that's your security objective, you protect it differently. And the last one that we really didn't talk about in here is availability, right? You got to make sure that if I have a system like Zoom, I have to be available for the student to go on to have, so I can give a lecture to them. So if you don't have the availability of the system, that is a security measure. Think about online banking. All of a sudden, everything, your internet is not working. You cannot watch TV. You cannot call someone. So that's definitely the availability is also a very important, basically availability of the system, availability of data that we are talking about in here. So cybersecurity usually is, I see more and more college and universities offering courses of that. Cybersecurity, you can get degree in that, but it's very, very new field. Again, it's very interdisciplinary. Usually it's you learn about it under computer science. You should learn it about under engineering and mathematics, also. There is a lot of, other fields come into place when you talk about cybersecurity, and it's a very, very practical field. You do not need a college degree. You probably can get a job in cybersecurity. As I say, right now, college, I see more and more college offering the degree, but not necessary. You could have different background. You can be a mathematician, you can be a biologist, you can be an urban planning, you can be in finance business, you can still do cybersecurity work because what they need is really certification in here. Now, I'm not sure some of this certification is worldwide or just unique to America, but in America, we basically have certification that we're looking for when you hire someone in cybersecurity. So again, cryptography is a very specialty field in cybersecurity. So it is protecting the confidentiality. When you want to protect confidentiality of your data, you have to have cryptography in there. So this is some basic intermediate certification you can get. There's some advanced one you can get, and there's some specialties one you can get. And depends on, it's very, very broad field, depends on your job, depends on what you do. Are you a left of the broom? Are you trying to prevent the broom? Or are you going to dealing with the broom? Or are you going to dealing with the right side of the broom? So are you going to incident response? It's going to be very different than risk assessment, your job, and your skill set is going to be very different. So that's why they're in this field. Is right now, I still see a lot of people hiring is really based on the certification, not their education or credential, not yet. Again, it's a very practical hands-on field. I do get the CISSP, that's me. ISC Square, that's actually an international consortium. So if you get any certification SSCP, from ISC Square, it's worldwide recognized. So CompTIA, I don't know whether there's a particular in America or in other countries, but Security Plus is a very basic certification that get your foot into the door, so to speak, when you have a Security Plus certification. Basically, you need to know a lot of networking, computer networking, and you need to know risk management too. You need to know, how much some of the technical techniques and concepts. If you're a system administrators, you're probably exposed to some of the security issue that you need to deal with. When you get to the advanced one, they're more managing the system than actually performing, doing some technical work on the system. There is some specialty. Is like, if you want to be an auditor of the system. Again, this is a compliance review in here. Lots of the time, the system, especially international system, they have to go through a compliant process. For example, your credit card. Every time you buy a credit card, it's international. It has an international compliance system in there, right? Called PCI. For this stand for PCI, point something information. I can remember. I can Google it. But it is, again, it's a very rigorous compliance process before they authorize or they certify, okay, you can use your credit card transition now, right? Everything you do online with credit card, and there's also a compliant thing. And so that's where the auditor come into places. The auditor come and audit your system and making sure that your system is compliant, with the standard. So then, they will protect yourself, also protect other people. It will be safe to use the system. There's forensic analysis. When you have the, right side of the broom, when you have that happen, then you're going to have, do forensic, and that's where specialty field too. Your best specialty field can get, you to the advanced career or, just a basic and intermediate career. It depends on really what you are doing in here. Software development, you can get offensive security certification professional. This is usually for offensive only. Software development, that I'm not sure there's a security certification for software, but you should have a procedure. You should have like develop your software in a certain way, in a secure way. So again, this security by design is very important concept to making sure that your system or whatever you're designing on your software is safe. UC Council is, I think, is international as well. This is also very famous, popular certification, very expensive in US, called CEH, Certified Ethical Hackers. So that's for people that do want to do penetration testing or try to hack into the system. We call them, what is that? We have the white hat hacker, we have the gray hat hacker, we have the black hat hacker. Black hat hacker is the one that will do malicious thing, it's illegal. White hat hackers is the one that you do ethical hacking and try to test your system and making sure that your system is not, have vulnerability and stuff. So incident response, that's also very, very specialized, that you can get a certification for that. And then, so this is like kind of like just like a really rough view about cybersecurity. I thought, you might want to know. And if you're interested in it, looking into some of the certification, usually it's computer science background, but again, when you do risk management, it's more management level, not especially management level. Any business have risk management anyway, but right here, we're talking about the technology, more technical risk management. And I have been in that field for 4 years actually, and doing compliance and risk management can't go hand in hand in there as well. So I hope you learn a lot within these 3 days, and that is concluded, my lectures today. And I have some additional reference book and textbook here that I use to formulate my lectures. So you can definitely look into it. That's, again, abstract algebra, number theory, linear algebra, they are all different branch of mathematics. Coding theory, is a little bit specialized too as well. Not everybody in mathematics you will take coding theory class. Usually it's for signal processing. Lattice, like, I never really learned it, but I heard about it many times, but I never really formally take a class about it. So that's tremendous broad, mathematical knowledge behind cryptography that now you see, and hopefully it will motivate you to learn more about mathematics. So I have 4 minutes for questions.
Okay. Thanks, Jennifer. We have the last one from Xavier Cabezas. I think you responded with the last part. So any book that you can recommend to start in the study of quantum cryptosystem. So you give it at the end of the lecture notes.
Yeah, at the end, there's only post-quantum cryptography. So if you want to learn more about quantum cryptography, right now there's only one. The quantum key distribution. So a lot of the quantum thing is not making it to the textbook yet. So I would say look into online, Google, and search, and a lot of white paper you will read. A lot of like scholarly paper, journal paper that you can read about it. That's not really formal, so to speak, and get into the textbook yet. So cryptography textbook, sometimes they will mention quantum cryptography, but again, it's not a very popular topic. I don't know why, but post-quantum, cryptography, that's actually a book. This book is published back in 2009, or 2006, I can't remember, that kind of thing. So it has been around for a long time. Only now, again, it takes a long time to invent a crypto system, because you have to go through a lot of tests and evaluation, making sure that it has perfect secrecy, right? For example, and then making sure that it's really do its job. And again, the theory is one thing, the implementation is another thing. So when people inventing the crypto system, they have this mathematical hard problem at the background, but then when you implement it, that's another story, and usually implemented by computer scientists, and usually it's a computer program. written in like, I don't know, C++, C#, those are the language that they use. So quantum cryptography is very, very, little you can find on the book. But post-quantum, you can find it in here. And all the other mathematical background, you probably can take classes, mathematical classes for that.
Okay, I have a couple questions that I did by myself. One is because in a moment in your talk, it seems like right now we have quantum computing in production, but I think it's not. So my question was if it can live together for a while, the quantum computer and the regular computers interconnected in the internet, for example.
Well, actually, yes. Great question. So I forgot to mention about that. When you do quantum cryptography, like quantum key exchange, you do have to have a classical channel, a classical communication channel. That's how Alice and Bob is, exchange a message. Hey, I'm telling Bob my selection of B, bit string B, right? So you do need the still need the classical channel to communicate. So you do need to both quantum channel and a classical communication channel. So another fun, interesting thing is IBM is actually have a quantum platform. I'm a little hesitant to call it quantum computer because quantum computer usually, you get your laptop is a computer, right? There's no such thing as a portable quantum computer, or quantum computer is like based on the core bits, and it has to be controlled in a very, very cold environment. Usually they will freeze down the photons into a manageable speed that you can control it. So IBM Q does have a quantum computing platform called Qiskits, and they have a really nice interface, and you can actually learn how to program, implement the Gopher and the Shor algorithm onto a quantum platform. But you can do it from your classical computer, from your computer. You just connect it to it. I'll put the link in here when I send you the note, Danny, then you can look about it. If you're a scholar, if you're a student, you can get a free account and you can play around it. They have all kinds of documentation that allow you to basically, program on their quantum computing platform. So now I didn't go into it, but you probably can learn it. They have a lot of documentation. You can learn about it. And in order to program into a quantum computer or quantum platform, you need to know about the quantum circuits. You need to know how to build a quantum circuits. So that's another new things that you have to learn. As I say, there's a lot of linear algebra behind it if you want to understand the map, but if you want to just do it, and they actually have a visualization of a block sphere too, and it's really cool. So there is a mix, so to speak, a quantum, computing platform and the classical platform, especially in the quantum key communication, quantum key exchange, you have to have a classical communication channel as well to communicate. So the quantum channel is only used to sending the photon. You cannot talk or speak or whatever. So you have to rely on the classical channel to exchange, other messages as well. So that's a good question.
Okay, I thought that it was silly. Anyways, we have another question. The lattice is a discrete space, isn't it?
Yeah,
Because
I think so.
you
Yes.
talk about the shortest, and then if it's continuous, you can make it as small as you want.
Yep, because it's the dots, right? It's shortest in the lattice. The dot is not always lining up that way. That's just where you need. It could be everywhere. So it depends on the space. So yeah, it's discrete.
Okay, we have a couple more questions. Giovanni Espinosa asked, which are the pros and cons of quantum cryptosystems in comparison with the classical cryptosystems today?
So again, quantum cryptosystem is really only that one, and only one thing is very popular right now is quantum key exchange. The pro and con for the classical crypto system today, the classical crypto system is it has been for a long time, right? The classical system is always based on the hard mathematical problems. So it gives you the computational security, right? While using quantum key distribution or quantum, I wouldn't say a quantum crypto system, but it's only used for quantum key exchange. That gives you the provable security. So it's a two different kind of security. One is based on computationally hard problem. We are betting on people that take a lot of time or take a lot of computer resources to break it. While in quantum, key distribution, you're not betting on that. You are betting on the quantum mechanics principle or properties to send message securely. That's not really and if one is better than the other, that's not really. So again, the quantum key exchange is only on the public key system as well. We are the private key system, right? Because you have the key exchange. That's the biggest problem that we have, to securely send the key to the other computational party, so you can decrypt and decrypt the system. While public key crypto, you see that a lot of them is also on the post-quantum crypto system, right? It's basically a public key system, because on the private key system, we know that yes, quantum computer can do the exotic search, but if I increasing the key size, it will count it will kind of like buy me some time. So that's why you see a lot of the post-quantum crypto system is really concentrate on the public key crypto system, because we can break the factoring, it can break the discrete log problem, and that's why we need to have a whole new set of computational hard problem to form to be the basis of our crypto system, post-quantum crypto system. So I hope I answered the question.
Yeah, just the last question from Xavier Cabezas. Just out of curiosity, is there something special about the names Alice, Bob, and Eve? I think that you mentioned something.
Yeah, Alex, Bob, and Eve is the most commonly used in the American textbook. If you study in Spanish, maybe they have a different Spanish name of that. It's just basically A, B, and C. That's just easy to remember. Alex and Bob, communicating each other, and you have Eve, and usually it's like represent evil, and then the eavesdropper, so it's Eve and that. There's nothing special for the name. You can say Antonio and Jennifer and whatever, but this doesn't sound to have that easy name to remember. It's just a common name that we use to illustrate the communication in here. Alex, Bob, and Eve. It can be any different name. You can name it person 1, person 2, and person 3 too. So.
Okay, so I would like to thank you, Jennifer, for your marvelous talk these 3 days and these 3 sessions. I would like people to just give a virtual claps in the session. So we are going to have the closure today at 4 p.m. local time. And in a few minutes, in 11:10, we're going to have the talk from Juan Mayorga Zambrano, compact embedding of p-sublet light cones on nuclear operations. So it's going to be in a little. Jennifer, thanks a lot. Thanks a lot.
You're welcome. You're welcome. I really enjoy talking about it. I can talk about this forever, as you see, and really, really enjoy sharing my knowledge, and hopefully give you some, rough idea, about cryptography and all this related topic behind it. And study math. Math is awesome. Take as many math classes as you can. It's very direct. Yeah, it's really cool. Understanding mathematics is really the key to understand the quantum mechanics as well. And lots of people complain about it so hard, but if you have a good mathematical background, you will have a better time to understand it. And it's really cool, quantum mechanics and stuff. So take a class and see.
Okay, so students, you get the advice. So thank you, everyone, and see you in the closure. Bye-bye.
Bye, everyone. I will send you the notes. I will add the link for the IBM Q. And then I will send you the note for today's lecture as well, Danny, so you can share with the other students.
Sure, thanks.
Great, you can stop recording now.